we have distance, we have displacement, we have speed, we have velocity, and lastly we have acceleration. Well, distance has to do with what? The space between 2 points. It is a scalar quantity and it is measured in what? In meters. It is measured in meters. We have displacement. Displacement is distance in a definite direction, meaning that displacement and distance are same, but they are not same. Distance is a scalar quantity, displacement is a vector quantity, and displacement is also measured in meters. Now we have speed. Speed is distance all over time. Speed is distance all over time, and it is a scalar quantity. Speed and velocity are same, but they are not same. Speed is distance all over time, and it is a scalar quantity measured in meter per seconds, m all over x, or a function of indices. I might as well write it this way. Now velocity is displacement all over time. Velocity is displacement all over time, and it is a vector quantity. It is a vector quantity, and it is also measured in meter per seconds, or a function of indices written this way. Now we have acceleration. We have acceleration. Acceleration is what? Velocity all over time. Velocity all over time measured in meter per second square. Meter per second square written this way, or a function of indices. Okay, now when the velocity of an object is collected over time and a graph is being plotted, when the velocity of an object is collected over time and a graph is being plotted with the velocity on the vertical axis and the time on the horizontal axis, that will give rise to what we call what? A velocity time graph. That will give rise to what we call a velocity time graph. Velocity time graph. Velocity time graph. Now, this is where I'm going to be concentrating on a velocity time graph. Now, what's a velocity time graph? Velocity time graph is just the graph of what? Velocity plotted against time. Okay? Now, we have what? The general representation of a velocity time graph. The general representation of a velocity time graph, we normally have it this way. For the graph, it normally looks this way. It normally looks this way, with the velocity on the vertical axis and the time on the horizontal axis, measured in seconds, don't forget. Now, this is the general representation of a velocity time graph. Yes. Now, before I go further, there are different parts that makes up what? This particular graph. Parts like this. You can see that the acceleration part, then this for constant velocity, then finally we have this retardation. Retardation. I just mentioned retardation. I forgot to list it among the terms. Retardation and acceleration are the same. The only difference is just that retardation is negative acceleration. That is fast. For one, being acceleration, it is increasing. For retardation, it is decreasing. So retardation and acceleration are same. And before I forget, retardation is also called what? Negative acceleration. Now, I said that there are different parts that makes up what? This general representation of a velocity time graph. So this is just a graph of what? Uniform acceleration. Uniform acceleration, when the velocity is increasing by equal amounts in equal interval of time. By equal amount, when the velocity is increasing by equal amount in an interval of time, we have this to be what? The uniform acceleration. We have this to be what? Constant velocity. Constant velocity. Then we have this to be what? Uniform retardation. So all this makes up what? The general representation of a velocity time graph. Now, that's it. a situation might arise when you'll be asked to determine what? The acceleration of the object from the velocity time graph. How are we going to do that? Now, let me start by naming the salient points on the graph. Now, we have this to be A. Maybe this is the time for this. Maybe we have this to be when the object starts from rest, which is normally designated as what? 0. Maybe we have this to be A. B, we have this to be C. Then D, E. We have this. Now, when the situation arises, whereby you are asked to determine what? The acceleration from the graph. What do? We just solve for because this is the part for uniform acceleration. We just solve for the slope of this part to determine what? The acceleration of the object. Now, how do we solve for the slope? How do we solve for the slope? Slope, or what we call what? Gradient. How do we solve for that? Remember that slope or gradient is given as what? Change in y all over change in x. Going by that now, y is normally vertical, x is what? Horizontal. Now, solving for the slope of this. That's from the graph, it is going to be what? The change in y, which is from here now, AE. For the acceleration, remember, acceleration. That is going to be AE all over what? Change in x, which is what? OE. That is how we determine what? The acceleration from the graph. If you are asked to determine what? The deceleration, or what we call what? Retardation. We also solve for the slope of the retardation part. So from here now, for retardation now, the slope will now be from the graph. That is going to be changing y, which is what? BD. All over changing x, which is what? CD. So with this now, we are going to determine what? The retardation from the graph. So that's by the way. Now, lastly, you might ask to determine what? The total distance. Total distance from the graph. What do? The total distance from the graph is given by what? The area under the graph. Total distance from the graph is given by the area under the graph. Now, what do we mean by that? If you are asked to determine the total distance from the graph, we simply solve for the area of the figure that we are having here. Now, this figure is a trapezium. So, if I want to solve for the total distance, I consider the area under the graph. I can solve for this distance in two ways. I can solve for their individual areas, add everything together to get what? The total distance. Or I solve everything wholly. What do I mean by that? There are three movements from the graph. Now we have this to be S1, S2, and what? S3. 3 parts of movement from the graph. Now, solving for the distance, what do I have to do? For the S1, the first part of the movement, the figure that we have here is what? A triangle. A triangle. Now, what I have to do is what? For me to solve for the area of this triangle, of course, it has a general formula. Half base times height. Once I determine what? The value of that, I come over to S2. S2 is what? S2 is a rectangle. The area of a rectangle is what? Length times the breadth. So, when I solve for that, I will get what? The distance for the second movement. For the third movement, we have a triangle as well. Half base times height. So, when the value I got here, plus the value I got here, plus the value I got here, I will sum everything together to have what? The total distance undergone by the what? By the object. Or, if I don't want to do it this way, I will simply solve it what? Wholly. What do I mean by that? The figure is a trapezium. The figure is a trapezium. So, the area of a trapezium, of course, you know the area of a trapezium. Now, when I solve for the area of a trapezium, I will get what? The total distance. The area of a trapezium is given this way. Half in brackets from this figure now. From here to here, we have this to be OC. OC plus what? You know, the addition of the two parallel sides, or rather the two opposite sides, plus from here to here, which is what? AB times what? The height. The height is what? From here to here, which is what? AE or what? BD. So I've just choose one, AE. So when I do this, I will still get what? The total distance undergone by the object from the graph. So that's it. Now we are going to pick questions. We are going to pick questions to illustrate what? Further. Now listen. Sketch a velocity time graph for a car moving with uniform acceleration from 5 meters per second to 25 meters per second in 15 seconds. Now, use the sketch graph to find values for I, the acceleration, I, the total distance traveled during the acceleration. Now, from the question, what do? I'll first of all make a sketch of what? Of the velocity time graph. Now, the question says that the car moved from 5 meters per second to 25 meters per second. Now, this is the time. This is the velocity. Measure the meter per what? Per second. Now, it moved from 5. This is the 0 region. That is when it is moving from rest. Now, moving from 5 meters per second to 25 meters per second. That means that I'm not going to start from here because this is when it starts from rest. So, from 5 to 25, I might just take it from here. It accelerated to 25. Picking this to be my 5. I'm picking this to be my 25. That is this point, to be my 25. Now, that happened in what? In 15 seconds. So this is what we are going to be having. Now, the first question says what? That we should solve. We should first of all make a sketch of this. Then we should solve for what? For the acceleration. Now, from what I thought, I said that acceleration, for you to determine the acceleration from your velocity time graph equals what? The slope or the gradient of the uniform accelerated region. Now, from here now, I'm going to be having that acceleration is equal or equivalent to what? To the slope. And the slope is what? Changing y all over what? Changing x. Now, from here, now introducing this, from here, the change in y, remember this is for the uniform acceleration, so I'm going to be concentrating here. Now, the change in y is from here to here, which is what? 25 minus 5. So that will give us what? 25 minus 5. For x now, x is from here to here. The value is now what? 15. That is, taking the value from the graph now is what? 15, from 15 to what? 0. From here to here, which is what? 15 to 0. It is equal to that. So that is going to be what? 15 minus what? 0. So this will give us what? 20 all over what? 15. 5 here will give us 3. Into this will give us 4. Which is 1.33, meter per second square. This is the acceleration. Now, for the distance from a velocity time graph is given as what? As the area under the graph. The distance in a velocity time graph is the area under the graph. So, from our graph now, what do we have? We are having what? A trapezium. We are having a trapezium. So, we are going to be solving for the area of the trapezium to determine what? The total distance. Now, the distance will now be equivalent to what? Area of the trapezium, which is what? From the graph, that is half in brackets. Remember, our trapezium can take different shapes, or rather, the same shape, but the position can be changed. But that doesn't change the fact that it is a trapezium. Trapeziums normally look this way. But that doesn't mean that I cannot draw mine to look this way. They are still same. So from the graph now, this is a trapezium. And that is going to be what? Half from here to here is what? 25. From here to here is 25. So from here to here is what? 25. So that will be 25 plus the opposite side now from here to here, which is what? 5 multiplied by what? The height. The height is from here to here, or from here to here, which is what? 15. So this is what we are going to be having, which will now be what? Half in brackets 30 times the height now, which is what? 15. Into this will give us 1. Into this is what? 15. 15 times 15 will give us what? 225 meters. So that is the distance. That is the distance. Thank you for this wonderful journey. I hope to meet you again.